a two-topic series, and we'll talk about centroids / center of mass. A brief overview of today's slides. We'll talk about, as I was saying a second ago, center of mass and centroid, both how to compute those for individual shapes as well as composite shapes. By the end of today's lecture, you should be able to answer two questions. Number one, what is a centroid? And number two, how do I find the centroid of a non-uniform shape? Those are probably two questions you've had all of your life. Today, great news, we'll get to answer them. So how does this material connect to what we've talked about so far? Well, in the past, you used to see problems that looked a little bit like this. You had a beam with a pin on the end on the left at A, and maybe a cable at CD. We talked about material stresses, and we understood that the size of cable CD, in terms of how thick its cross-section is, will impact how strong the cable and how strong the system is. The larger the cable CD is, the more surface area it has. And because stress is equal to force over area, if the area is greater, we will have less stress and therefore a stronger system. That's good news. Now, that would just be looking at the cable. Something we haven't yet considered yet is another very important piece of this whole system. What do you think that is? Well, that would be the giant beam that's sitting right here. So we've never really thought about what the beam is made out of. So it's going to be important for us to figure out how to do that. So the question we might have for our beam is, so a question you might have about the beam is, what does its cross-section look like? Is it just a rectangle? Is it a square, or is it an I-beam? Well, which of those things would be best? That's the goal of what we're going to be talking about today, is that eventually, by looking at the cross-section of a structure, we'll determine not only things like stress, but also other aspects related to structural design, such as buckling. So let's introduce ourselves to the topic of center of mass and figure out what is this all about. Really, centroid and center of mass, at least from my perspective, are interchangeable. For a centroid, it's essentially the center of mass of a geometric object of uniform density. And for a center of mass, probably we are all pretty familiar, it's essentially the point of balance where a system of mass will more or less balance about. So you can see in our particular example right here, we've got ourselves a seesaw, and that seesaw is perfectly balanced right along the middle because it has equal weight on the left side and equal amounts of weight on the right side. That makes this point right here in the middle the geometric center, or the center of mass. This thing down here, which some of you might be familiar with, has a lot of weight right here in the wing tips, such that this point right here inside our eagle's head is actually the balancing point of our eagle. So when we look at the equations for this, essentially what we can see is that we have a centroid, or a center of mass, along three different axes, both the x, the y, and the z axes. If you look, the x-axis, center of gravity or center of mass, would refer to the distance from x equals 0 to the point of the center of mass along the x-axis. The y center of gravity would refer to the y-coordinate of the center of mass, and the z center of mass would refer to the z-coordinate of the center of mass. Pretty straightforward. Now for the example that we have here on this slide, you can see that it's pretty straightforward. Essentially it is just a man balancing a stick, and effectively we're only finding the center of gravity along one axis, which would have been perhaps the x center of axis. But had the shape been more advanced and been a three-dimensional shape, you would have to compute the center of mass in all three dimensions. So you might get a little bit worried and think that these equations look all new and scary, but the truth is that you've actually been utilizing these equations for a very long time, especially as an engineering student. You always have to figure out what is the average of the test that you just took, especially for Chem 135, because the average on that is probably not particularly good. So you want to know where your quiz stands relative to the average score of the average student. The equation that you use for average on a test is as follows. And if you look, it's actually pretty much the same exact equation as the center of mass equations. Really, the idea is that the centroid, or center of gravity, is where the average of all the mass is. And let me explain this a little bit more closely. So if we look here in our particular example, you can see that our x center of gravity equation is going to be equal to some xi, which is essentially some distance away from a chosen datum point, multiplied by the mass of that particular piece divided by all of the mass along the x direction. The idea is that this will work for a system of masses. So if we look here, our average equation is actually the same, and let me explain why. The average on our quiz is going to be equal to more or less the center of mass of the quiz. And the test score refers to how far a student's score is away from some chosen datum point. Mass, as you might guess, is very much related to the number of students. So if you had a lot of students get a 100, then the average is going to be very close to a 100. So essentially you'll be multiplying the number of students by the score that they got and dividing that by the total number of students in the class. So the number of students is very much related to the mass, essentially how much there is, and the test score is relative to this position x, which is essentially how far is it away from some chosen point. When we show the next slide, hopefully this will become more clear. Use your skills in computing the averages of quiz and compute the average of this quiz right here. Let's say that 4 students got a 70, 3 students got an 80, 2 students got a 90, and 1 student got a 100. I'll give you a minute to calculate this, and I'll let the timer go. Alright, I'm sure by now that you've been able to compute the quiz average, but let's just go over it to make sure. To compute the quiz average, what you would be doing, as I explained before, is you'd be computing the number of students that got that score, got a particular score, multiplied by the score that they got. So the number of students will be multiplied by the test score. So in our first case, we have 4 students got a 70, 3 got an 80, 2 got a 90, and 1 got a 100. As I was explaining in the last slide, the test score is relative to how far the students did away from some datum. Here we're measuring all the scores from a base score of 0. So we've got 70, 80, 90, and 100. And last but not least, we divide all of this by the total number of students there are in the system to find what the average is, which was a total of 10 students. What you see is that the answer to this question is 80, or that the average on this quiz is an 80. Well, one way that you could have done this actually without doing pretty much any calculations is to have realized that this shape of the quiz is actually a triangle. And if the shape of the quiz was a triangle, we know from geometry that a triangle has a center of mass 1/3 from the bottom. So if you look at our particular question that we just did a second ago, what you may realize is that from 70 to 80 is 1 unit, from 80 to 90 is 1 unit, and from 90 to 100 is another unit. So 1/3 of the units from the bottom would have arrived for us to have an average of 80. Again, this relates back to the center of mass of a system, which is again just essentially telling us the following, which is that how far are you away from some given point, xi, multiplied by how much stuff there is at that point, very similar to how many students you might have. To solve for the average location of the mass, you divide by all of the mass, and those two equations end up being more or less the same. This is all well and good for all sorts of shapes that we may know, like a square, a triangle, or a circle. There's also tons of other resources out there that tell you the shapes of other common, the center of mass of other common shapes. But what might you do if you were given an unusual shape, or rather a composite system of shapes? Well, let's look at the next example. Here we have a uniform beam that's 5 kilograms, and we're told that it holds two masses of 22 kilograms and 15 kilograms as shown. Find the center of gravity of the system of objects from the left edge of the board. Now what I want you to do is utilize this little equation right here and what we just talked about to figure out what is the center of mass of this 3-mass system. And I want you to do it from the left edge of the beam. So I'll give you a minute to work on this, and then we'll go over the solution when the green question mark falls to the bottom. Alright, let's go over the answer. So, the first thing you'll want to do is you'll set your datum as I instruct you to do just a second ago. And you'll say that the left edge of the beam will be treated as x equals 0. That'll be what we measure everything from. Now what we do is we use the following formula to compute the x center of mass, which will be m1 times x1 plus m2 times x2 plus m3 times x3 divided by the total mass. When you plug everything in, essentially what you'll see is that we have our 22 kilogram piece of mass, which is located 1 meter away from our datum point. You have our 5 kilogram piece of mass, which is the beam's mass itself, times 3 meters away. And you have 15 kilograms times 4 meters, which is the third mass, how far away that is from the datum. Maybe you're confused for a minute about why this case is 3 for the beam. But remember that our beam is 6 meters long, and we know that the center of mass of any rectangular object is always going to be in the middle of that rectangular object, which would be at x equals 3. When you do all of this math out and you compute the center of mass of the system, you will compute that it's 2.3 meters from the left edge. Now, you could have solved this problem a different way. You could have assumed that, let's look and say that the datum point was x equals 3. That's totally fine. The datum point you choose is pretty much arbitrary, or the decision is up to you. Had we done that, we would have still had all of the pieces of mass, except we would not have to include the beam anymore. The reason would be because the distance from the beam's center of mass to our chosen datum would be 0. Therefore it cancels out. However, the beam still does appear in the bottom of the equation because that is part of the mass of the system. When you do the math out, you would get that the answer for the center of mass is negative 0.7 meters from x equals 3, which would basically tell you that our center of mass was 0.7 meters to the left, which, if you remember our answer from before, is essentially the same thing as saying that it's 2.3 meters from the left edge. We compute exactly the same answer regardless of the datum that we choose. Alright, now what we'll talk about is how to use center of mass to compute the centroid of shapes that are composite and have multiple shapes, such as different beams and structures. In ENES 102, oftentimes you'll be working with composite shapes, or shapes that have multiple different combinations of things. In this particular case, you can see that we have two I-beams. Both have the same shape, however, on the one on the right has a much larger base. As a result, you can see that the center of mass of that shape is shifted more closely to the bottom, or where their mass is at. As we've discussed before, the center of mass of a shape is going to have a lot of impact in terms of the structural integrity of a system, especially in a failure method called buckling, which would be the bending of this particular member. So, the formula that we've used so far to compute center of mass is the following. The sum of xi times mi over the sum of mi equals the x-coordinate of the center of gravity. What we're going to do now is use the fact that most of the shapes we're going to be working with in this class have uniform density. Therefore, we'll replace essentially the mass with the volume. And given that we're only looking at two-dimensional shapes, we'll actually get rid of the volume and just assume that we're looking at only the area. Therefore, our new equation that we'll begin to apply to all of our example problems and on the exam is going to be the following. That the x center of gravity is equal to the xi, so still using a measurement from some datum, but in place of the mass, we're using the area, which essentially is just telling us how much of the material do we have some distance away from the point that we're looking at. So our equation is fundamentally pretty much the same. However, instead of mass, we'll just be using area, which will be much easier for us to compute moving forward. So now we just have two equations in this class that we'll be looking at. And to compute two-dimensional centers of mass, we'll be looking to find the x-coordinate and the y-coordinate of the center of mass by using the area equations. You can look at this particular example here and see that it just looks like a pretty amorphous gray blob. But if you look more closely, you would learn that this example question would ask you to solve for the center of mass of none other than this crazy shark. So, the first step in any question like this is 1. Don't get scared. It's actually to make the shark look like something else entirely. Use your imagination and change the shark into something that's much less frightening, which may be two triangles and a blue rectangle. So the first step in any single center of mass problem, especially on the exam, is break down the larger composite system of shapes you have into the fewest number of shapes possible. So in this particular example, I broke the system down into 3 shapes. A purple triangle at the top, which I've labeled 1, a blue rectangle, which I've labeled 2, and a green triangle, which I've labeled 3. The next and most important step that you're going to want to do is you will always want to make a table that looks like this right here. This table is going to allow you to keep track of everything and compute all of your calculations much more easily. So the point of this table is essentially you have a column for the shape that's in question that you're going to be looking at. So our first column is shape, and as you see we have 3 shapes. We have the triangle, which is purple. We have the rectangle, which is blue. And we have the third triangle, which is green. What we want to do is solve for the area of these 3 shapes, which we can do the following. The area of the purple triangle is 1/2 3 times 3, the base times the height. The area of the rectangle is 7 times 12. And the area of the last triangle is 1/2 2 times 12. The total area is 100.5. What you'll want to do on an exam is you'd want to solve for those 3 areas, and you'd want to put them at the bottom of your table right here. The other thing that we know we are going to need is this down over here. And the way that we compute the xi times ai total sum is we're first going to have to figure out the location of the x centroid for each of the three particular shapes that we've identified in our question. The good news is for us is that the three shapes we've identified are very easy. They're triangles and rectangles. And we already know where the center of mass of each of those shapes is because those are very common shapes. So we can plug the things that we know into our table and show what we get. So if we look right here, what we can see is that the center of mass of this triangle here that's purple is a value of 1. That value of 1 comes from the fact that our triangle was 3 meters wide. Our center of mass is 1/3 that distance. And essentially what we're doing is we're measuring all of our points, or all of our distances, from this bottom right corner. If we look at the rectangle for 3.5, what we see is that our rectangle had been 7 meters. And we know that the center of mass of a rectangle from our x equals 0 is going to be equal to 3.5. And last but not least, our final triangle, which we have on the far right edge, we can see has a center of mass of 7.67. The reason being that that's going to be 7 plus 2 over 3. And we know that 2 over 3 is 0.667. And that's the center of mass of this shape right there. What we then do is we multiply our number here, 4.5, for the area, times the centroidal distance. That's what we're computing right here in this column. When we do that for all of the shapes, what we eventually find is the x times a for each shape. Essentially, what's the average of that shape going to have on the entire system? Again, when we bring back the area and we look at what our equation is for the whole system, we know that to compute the x center of mass, it's going to be the x times a sum. So essentially, it's going to be our total that we've computed down here is going to be our top portion right here. And then our area is going to go on the bottom, right there. So when you see this play out, the answer becomes that the x center of mass of this whole system is 3.88 meters. And this should make some sense because as we look again at the whole structure, if the center of mass is 3.88 and our whole structure at the bottom, if you look, was 7 plus 2, it was 9. We know that the center of this shape is at roughly 3.5, so roughly about here. And actually we've got a bunch of mass kind of more to the left over here, and this mass over here is to the left. So if we go back to our final answer at 3.88, it makes some sense that the center of mass of our shape is just slightly to the right of the center of mass of this rectangle. Now, we can do the exact same thing we just did for the last question, but now we want to solve for the y center of mass for this question. So our area remains the same, and the only thing that we need to pretty much change this time is we just need to look at the location of the y center of mass for each of our shapes. Given that this purple triangle has a height of 3, we know that from the bottom of that triangle, its height, center of mass, is 1/3. But we have to add that 1/3 to 12 to get the distance from the bottom left datum point, which was the point that we're measuring all of our numbers for center of mass from. For our rectangle was 12 tall. So the center of mass of a rectangle in the y direction is half of that height. And last but not least, for our final triangle, we have that the height of that was 12. So 1/3 of 12 gets us a value of 4. Again, what we do is we take our value here of 4, we plug that in there, and we multiply that by the area of that particular shape. And we do this 3 times for all of our different shapes, and we develop a final answer and get that the total y of each shape times the area of that shape yields us a value of 610.5. To compute the center of mass of this system in the y direction, we simply take the sum of yi times ai divided by the total area for the system, and what we compute is a final answer that y is equal to 6.07 meters right here. And again, going back to our intuition, we can see that our rectangle is 12 tall. That's one of the largest pieces of the system. It has a very large area. And our other triangle is the next biggest thing. So what we can more or less gauge from this is that our center of mass is going to be just above the center line of our rectangle. And this should match what our expectations are. Now the good news about center of mass is that it does have some checks. You can be able to use common sense to figure out if your answer makes, well, sense. So if you got that your center of mass had been y equals 17, that would tell you that the center of mass of your system is up here, which, how could that possibly make any sense? Because that is not even in the shape in question. Had you gotten your x center of mass was something like over here, you should look at that and think, that doesn't make any sense either, because that is way to the right, and I can tell that most of my mass is to the left. So by using common sense and the equations and this handy-dandy little table at the bottom, you should have no problem solving for the center of mass of most shapes and composite shape systems. And as you move forward in this material, what you might realize is that this could be useful to identifying distributed loads and where the net force of a distributed load acts. Just another way of applying this material to something we've already seen before. And now what we'll talk about is what you do when you have holes or anti-shapes within the system. So the way that you handle a composite shape that has a hole in it is actually quite simple. We use the exact same methodology that we did before. Again, what we want to do is we want to identify the number of shapes in our particular question, which in this case is quite easy to realize. There's two things. There is a circle and there is a square. What we'll do is we'll compute the area of each shape. The area of the square would be, 4 by 4, 16 meters squared. The next thing we want to do is identify the area of the circle, which would be pi r squared, which would be pi times 1 squared. Now here's where the difference comes in. Essentially what we want to do is for negative shapes, we want to make sure that we're computing the area as a negative, and actually will be subtractive in our table that we were using before. So what does that look like? Essentially, when we add up the areas of these two shapes, we won't get 16 plus 3.14, we'll get 16 minus 3.14, as you may have guessed. And when we plug that into our table over here, we can see that again we'll be doing the shapes in question, which are the square and the circle. We know that the centroid of both of these shapes in the x direction is at 2 meters because this system is symmetrical, and we know that the answer for the center of mass should be pretty much right in the middle of our system. What we can see happen is that when we take the area, we will have 16 times 2 for the square, gets us a positive 32, whereas for the circle, we actually will get 2 times 3.14, but this will be negative because we have a negative area right here, multiplied by our center. So what we get out of our solution for the x center of mass of this particular case then is the summation of 32 minus 6.28 divided by the area 12.86 that we had at the top. And our final answer is what we should expect it to be, which is that the x center of mass of this system is equal to 2 meters, or right smack dab in the middle. So this is how you'll approach solving composite problems and how to solve problems with negative areas. The final thing that we'll do in this lecture today is we will talk about an old exam question which has multiple shapes in it, and I'll discuss how we're going to solve for the centroid, which is going to be the x and y bar for each this system. All right, here we have an example center of mass question that you might see on an exam. The first step that you want to do is you want to draw your table down here. In our table, we will have a column for the shape that we're identifying, the area of that shape, the x center of mass location, the area times the x center of mass location, the y center of mass location of each shape, and the area of each shape times the y center of mass location of each shape. The one thing that we were given up here is the quarter circle. We are told what its x bar and y bar are, and they are the following. They're 4r over 3 pi. And we can see that the area of a quarter circle, no surprise, is pi r squared over 4. So the first step that we have to take in all of these problems is to identify how many shapes we have. So it's usually a good idea to take out a marker or something of a different color if you have it, and try and identify as few shapes as you possibly can. So the one thing that we should be able to see is that we have this nice square acting in our problem. So we'll say that our shape number 1 is going to be our square. Shape number 2 and number 3 are both going to be negative shapes. We can see that here we have a hole in the middle, which is 60 millimeters in radius. And we also have this quarter circle up here in the top right. We'll say that both of these are negative shapes that we will factor in down over here. And it might not even be a bad idea to have these shapes start out as red so we don't forget to subtract them from our equations. So our second shape we will say is the circle, and our third shape we'll say is the quarter circle. So we'll just fill those details in right here. All right, now what we need to do is we need to compute the area of everything. Well, the area of a square is just base times height, or width times height, which in this particular case is going to be 100 plus 140 times 80 times 160. This is going to get us 240 times 240. Or 240 squared. And that gives us an area of 57,600 millimeters squared. Now what we do is we compute the area of our circle, which is pi times r squared. That's going to be pi times 60 squared in this particular example here. And we know that the value of the area here is going to be negative 11,309 millimeters squared. Now the reason I'm drawing that in red is because this is a negative area. It's a hole in our shape. So it's going to be important to not include that in the rest of our addition of all the areas. So last but not least, for our quarter circle, it is pi r squared over 4. The radius of our quarter circle we are told is 120. So this becomes pi times 120 squared divided by 4. We get an area for this one that is also negative because it is a hole of, ironically, negative 11,309 millimeters squared. So it's the exact same as above. And adding all of this together, we get that the total area will be 57,600 minus this area will get us an area total equal to 34,982 millimeters squared. Now our next step is going to be to figure out the x location of all of these things. So what we're going to be doing is we're going to be taking the centroid from this bottom left corner, which we're going to set equal to 0, 0, which you can see is actually the case not only based off of my judgment, but also based off of the judgment of this problem. Because you see we have the y-axis right here, and we have the x-axis right here. So as a result, that bottom left corner actually is 0, 0. Sometimes you'll see in a problem that the y-axis might be in the middle of the shape, or that the x-axis might be in the middle of the shape. But here we don't have that. Our shape starts in the bottom left corner. So to compute the x location of each, We pretty much know that for a rectangle, it's going to be in the center. So we're measuring how far along the x-axis do we have to go until we find the middle of that particular shape. Well, for our square, that is going to be at 240 over 2, or 120 millimeters. For our circle, we're told that from the x-axis to the center of the circle is 100 millimeters, so we're good there. And then our quarter circle is a little bit more interesting. We know that for the quarter circle, x bar and y bar are equal to 4r over 3 pi, as measured from the flat side. So essentially, what we can compute here is that we have 4 times 120 over 3 pi. What we get here is that this is a value of 51. But remember, this is from this side. So we know that the center here is 51 from that side. But really, what we want the answer from the left side to that point. So the way that we're going to do that is we're going to say 240 minus 51 is actually the xi of this shape. And that gets us a value of 189 millimeters. So now what we'll do is we will compute AI times xi. So we're just going to take the value in this column and multiply it by the value in this column to get this. So when we do that, what we'll see is we get a value of 6,912,000 in this column. And in the other columns, we're going to get a negative because the negative area multiplied by a positive number gets us a negative number. So this allows us to just kind of keep things straight again. So now we multiply these two numbers here and we get negative 1,130,900. Over here we multiply this by 189 and we get negative 2,137,401. Now what we do is we add up this whole column here. So we do the sum of everything in this column. Sorry, that's a messed up looking sigma. But when we add all of these things together, we get a total of 3,643,699. All right. Remember that for the x bar, for our whole question, it's equal to the sum of xi times ai over the sum of ai. Well, for our example right here, we basically take this number right here and divide it by this number and we get the answer. So now we'll plug in 3,643,699 divided by the area, 34,982. And this gets us a value of 104.1 millimeters for our x bar. And we'll just write x bar down here again, and we will circle our answer. Now, if we want to check our answer and see if it makes sense, I think it does, because if you look, our whole system right here, the middle is normally at 120. We've got this big old chunk of area missing over here, and we've kind of got more area missing even to the left. So as a result, we definitely have more mass over closer to the left side than we do on the right side of this system. So our center of mass, it makes sense, one, that it's in the shape, and that it's probably a little bit to the left of the center where it would be normally. If we repeat this process in the y-axis, we can see from the bottom to the minimum of our square, we have 240 over 2 again. So it gets us a value of 120 millimeters for the centroid of this shape here. We can see that the center of our circle is 80 millimeters from the y-axis. And for this shape right here, we would again get a value of 51, and that value of 51 would be measured from the top of our quarter circle going down. So again, what we need to do essentially is take 240 minus 51, and again we get the same exact number that we did before. We get 189 millimeters. And again, this just comes from this equation right here. So last but not least, we multiply our area times our yi columns, and we get all of our new numbers, which if we do that, as you can see, we have all the same numbers at the top. So our y times a up here is going to be the same value that we got before. And now we're going to repeat the process for our circle. We get a slightly different number this time, negative 904,720. And down here, we get the same number that we did before, which is negative 2,137,401. Now all we have to do is we sum this whole column right here. Draw my sigma better this time. So sum of the AI, yi, that's going to be equal to 3,869,879. And to solve for the y bar of the shape, that is just going to be the sum of yi times ai over the sum of ai. So we plug this number in, divided by our area that we had from before, and we will get our value, which is the last part of this problem here. And the value that we get is equal to 110.6 millimeters. And again, we'll just write our y bar here, and we will box our answer. And that is it. That is how you solve a center of mass problem, typical to an exam, based off of both the x bar and the y bar, and having kind of an unusual shape here, which is a quarter circle. And that's it.